a look at finding a derivative of something a little bit more complex. Here's our function, and so we have to put this into every place we see x, and that's why you see this. Minus f of x all over h. Now, when you're working with fractions, you've got to get a common denominator. So what we're going to do is we're going to be multiplying numerator and denominator here by 2 plus 8, 2 plus x, 2 plus x. And then right here we're going to multiply the numerator and denominator by this denominator, which is 2 plus x plus h all over 2 plus x plus h. And so that's why you're seeing this right here and this right here. That's these two right here. And then the common denominator is this. And remember, I can multiply this by 1 over h, and then I can multiply the numerator by, as soon as I get all of this simplified, I can multiply that by 1 over h. And that's why you see the h here and this denominator right here. Okay, we're going to expand it and we're going to simplify. And after we simplify, we're going to allow h to go to 0. And this is what we get right here. Okay, other notations for derivative. So this is the one we've been using quite a bit. But we can say y prime. We can say dy dx, and dy dx is an offshoot of this idea of slope. So when you take the limit as delta x goes to 0, we get this instantaneous rate of change where the triangles, the deltas, turn into d's, meaning we have actually taken the limit. Instead of y, you can use f. You can use it like an operator. You can say, I'm about to take the derivative, just like you're about to take the square root or you're about to square. And again, this is an indicator that you're going to take a derivative, and this is an indicator you're taking a derivative with respect to x. So differentiation operators, because we are using an operation. All right, now when you use this notation right here, it's not clear when you're trying to evaluate at a certain point. This is really nice because it says f prime and it tells you where you're going to evaluate the derivative. So when you're using this fraction form, what we use is we use this bar down here, and then we say this is what we're going to substitute for a to get the instantaneous rate of change at a particular point. So this is the notation we use instead of this. A function f is differentiable if f prime of a exists. If it is differentiable on the open interval, it is differentiable at every number on the interval. Okay, where is this function, the absolute value, differentiable? Okay, which means when can I get a derivative? Okay, and so I can get a derivative here, I can get a derivative here, I can get a derivative here. You can see all the derivatives right here. But right here at 0, I can't get a derivative because I will not be able to evaluate here at 0. You can see there's this discontinuity going on right here. So where is a function differentiable? It's differentiable everywhere except for 0. So negative infinity to 0 and 0 to infinity, but not at 0. 0, we don't have that. Okay, here's our next theorem. If f is differentiable at a, then f is continuous at a. So if you can find a derivative, then there must be continuity at that point. And here is the proof of that. What we're going to do is we're going to start off with two things that are equal. Actually, this was f of x minus f of a all over x minus a equals itself. And all we did was take this part and bring it to the other side. Or if you want to think about it, take this and divide it on both sides and you have two things that are equal. Now we're going to take the limit of both sides And when we take the limit of both sides, we're going to concentrate on the right-hand side. The limit of the product is the product of the limits. And this part right here is going to go to 0. And this part right here, you should be able to recognize that it's a derivative. So this expression is equal to 0. All right, now we're going to start off with a limit as x approaches a of f of x. And we are going to write it out by adding and subtracting f of a. So in essence, if you were to reduce this, you just get back to what you started off with. And we're going to separate this. The limit of a sum is the sum of the limits. So we have this sum of these limits. This actually matches this up here. So we know that this thing right here is f of a, and we know that this expression is 0 right here. That's 0. So what we're saying here is that this answer is f of a. Now let's start from the beginning. The limit as x approaches a of f of x is equal to f of a. Now what are the requirements for continuity? One, that the limit exists. And the limit does exist because it has an answer. Second, that f of a exists. And f of a does exist. There is a number for it. And the third requirement is that the limit equal the value, which is what we're showing right here. And the only reason we were able to do this is because we were able to say that we had a derivative. When you have a derivative of a point, we're able to go through this process and prove that the differential continuity exists. Okay, the converse of the theorem, though, is false. You can't say, you can't go the other way. If function is continuous, then it is derivative does not make sense. And we know the counterexample is the absolute value function. The absolute value function is continuous, but we know it's not differentiable, especially at 0. Okay, how can a function fail to be differentiable? Well, it'll fail if there is a corner, or if there's discontinuity, or if we have a vertical tangent like this. So those are the places where a function can fail to have a derivative. How can a graphing calculator show differentiability? Well, if you go in and close enough, you zoom in, and if you see this smooth curve, which ends up looking, more and more linear, then you know you're going to be able to have a derivative. But if you get closer and closer in, and there's these corners or rapid changes, then it's showing you that you can't have a derivative at that point. Higher derivatives, like a derivative of a derivative, can be written this way. So you have a derivative, and you take the derivative of it. It'll be a second derivative, and it can be shown this way, or we can use the operator notation. And when the operator notation is being used, then it looks something like this. So remember, the first derivative looks like this, and the second derivative will have these exponents here. All right, let's take a look at this function. We found its derivative. It was right here. And let's go ahead and find the second derivative, which means that we're going to go back to the definition. We're going to put this x plus h into this function. And then again, we're going to have f prime of x, which is this, all over h. Go through the process of simplifying, and we're going to get a derived function of 6x. Now let's put it all together. Here's f, which is a cubic. Here's its derivative, which is a quadratic. And here's the second derivative, which is linear right here. And all of them are describing the slopes of the previous function. All right. Now that we're talking about higher order derivatives, remember the position function. The first derivative is velocity. And if we take the derivative of velocity, which is the second derivative of position, it's called acceleration. And this is how we can show it. Now, a third derivative would be the derivative of a second derivative, and it would have this triple. derivative of a second derivative, and it will have this. We can continue to take derivatives, but then all of these marks up here are going to get kind of crazy. So after the third derivative, we start using a number in parentheses up here to indicate what derivative we're using, so we don't have to count them all. And let's take a look again, this function that we've been working with. And we got to the second derivative when we had the second derivative equaling at a slope of 6. Oh, here's the second derivative right here. And if we figured out the third derivative, we would find the answer is 6. And so the third derivative in this particular problem ended up being a constant. If we were to continue, the derivative of a constant would be 0 here. Now, is there a physical application for a third derivative? And the answer is yes. Position, first derivative is velocity. Derivative of velocity is acceleration. The derivative of acceleration is what we call jerk, a rapid change in acceleration. And I think we have all experienced that when we take our accelerator and there's a rapid change, that we do move or jerk in the car and have that feeling. This is the end of the screencast.